Welcome to the deep dive. This is where we cut through all the noise and really deliver those key bits of knowledge straight to you. And today we're kicking off something pretty special, our CSWIP 3.1 exam prep series. Yeah, this deep dive is specifically for you if you're gearing up for that CSWIP 3.1 Welding Inspector Exam. Think of this as, your personal guide to mastering the core ideas, figuring out the why, and getting confident with those exam-style questions. So, our mission today, pretty straightforward. We're going to tackle some really critical multiple-choice questions, the kind you'll definitely see. But we're not just giving answers away. No, we're going to break down why the correct answer is right, what's the knowledge behind it, what does it mean for you as a top-notch inspector. Goal is simple. Give you clarity, give you confidence, not just memory tricks.
Absolutely. And that's the real value, isn't it? It's moving beyond just knowing the answer. It's understanding the reasoning. Why is this action needed? Why this particular test? This isn't only about passing. It's about becoming a really effective, knowledgeable inspector who understands the consequences. Critical thinking is key.
Couldn't agree more. Okay, so let's jump right in. First question gets right to the core of what an inspector does, a real fundamental. Here it is. If a welding inspector detects a type of imperfection not allowed by the application standard, he must. Okay, your options are A, request further NDE. B, reject the weld. C, prepare a concession request. D, reject the weld only if he considers it to be harmful. Right. Take a second to think about that one. Seems simple, maybe. Let's unpack it. So what's the absolute must-do for an inspector here, and why is it the only right move?
Well, this question, it perfectly highlights the inspector's core duty. The answer, no question about it, is B, reject the weld. What's really crucial here is how this defines your primary role. If something is not allowed by the application standard, well, that standard is the rule, full stop. It's not up for debate, not your personal judgment. The standard says no, then it's a fail. Compliance is everything. Your job is simply to check if the weld meets the requirements. If it doesn't, it's non-conforming, period. Now, let's quickly look at the others, why they're wrong in this specific moment. Option A, request further NDE. Generally, NDE would have already found this imperfection. More NDE won't make an unacceptable flaw acceptable.
Right, that makes sense.
Option C, prepare a concession request. This is a common mistake people make. Concession requests are a thing, yes, but they come later, and they're not started by the inspector. Your job is to find the non-conformance. It's the fabricator, maybe the client, who then decides if they want to ask for a concession. Not your call.
Okay, so the inspector reports the finding, and then others decide on concessions.
Exactly. And IT, reject only if he considers it harmful. Absolutely not. That defeats the whole purpose of having a standard. Standards exist precisely to remove that kind of subjective, potentially dangerous judgment. Your opinion on harmful is irrelevant if the standard says reject.
That's crystal clear. The standard is the objective benchmark, removing bias. That puts a lot of responsibility on the inspector to uphold it.
It does. You're guarding safety, quality, the whole industry's reputation, really. Your integrity is key.
Okay, moving from rules to tools. Let's talk about something every inspector uses, the magnifying glass. Practical stuff now. Here's the question. BSEN 970 allows the use of a magnifying glass for visual inspection, but recommends that the magnification is options A, x2 B, x2 to by 5, C, x5 to by 10, D, not greater than by 20. Right, this one's interesting. It's not just more is better, is it? What's the sweet spot here, and what's the logic?
Yeah, this is a great one. It shows how standards think about practical things like, ergonomics and just plain effectiveness. The correct answer, according to BSEN 970, that's the European standard for visual checks on fusion welds, is B, x2 to by 5.
x2 to x5. Okay. Why that specific range?
Well, it might seem a bit counterintuitive. You'd think tiny flaws need huge magnification.
Oh, yeah, kind of.
But think about trying to read a map with a super powerful microscope. You'd see amazing detail in one tiny spot, but lose all sense of where you are. We call it magnification tunnel vision, this x2 to x5 range. It's the best balance. It gives you enough detail to spot things like fine cracks or undercut, but crucially, it doesn't shrink your field of view so much that you can't scan the weld properly. Go too high, say by 10 or by 20, and your view is tiny. Scanning is slow, tiring, and you easily miss the bigger picture. Plus, it causes serious eye strain over time.
The eye strain factor. Didn't think of that.
Definitely. And too low, like just x2 maybe, you might miss very subtle things. So x2 to x5 hits that sweet spot. Effective, efficient, and actually usable for long periods.
Magnification tunnel vision. I like that. It really paints a picture. So these standards are quite practical, thinking about how the job actually gets done effectively.
Exactly. They have to be.
All right, let's switch focus again. From looking at the surface to testing what's inside, specifically a material's resilience. Question 3. Which mechanical tests can be used to measure the toughness of weld metal, HAZ, and parent metal? Your options: A, macro.B, nick-break.C, hardness.D, Charpy impact. Okay, think about these. We're talking toughness now, not just strength. How something behaves under impact. What's the test, and why is toughness so vital in welding?
Right. Another really key concept. Toughness is critical. And the correct answer, the standard test for measuring toughness across the whole weld area, weld metal, HAZ, parent metal, is D, Charpy impact.
Charpy impact, okay.
So first, what is toughness? It's not just strength. It's about a material's ability to absorb energy, to deform a bit before it fractures, especially under sudden load like an impact. Think hitting something with a hammer versus slowly pushing it. A tough material won't just snap half.
Okay, resistance to shattering, basically.
Pretty much. And that's vital for anything operating at cold temperatures. Think offshore structures, cryogenic tanks, or under dynamic loads. Places where brittle fracture would be catastrophic. The Charpy test simulates this. You have a small, notched bar of the material. A swinging pendulum hits it, breaks it, and you measure how much energy the sample absorbed in the process. It gives you a number, a direct measure of that impact resistance.
I see. And the other tests, why aren't they the answer for toughness?
Good question. A, macro tests. They show you the big picture of the weld structure. Fusion, big flaws. Useful but no mechanical property numbers.
Right.
Nick, break. Simpler test. You notch it, break it, look at the fracture face for defects like pores or lack of fusion. It tells you if there's something wrong inside, qualitatively, but doesn't measure toughness energy.
Got it.
C, hardness. Measures resistance to scratching or indentation. Hardness and toughness are related often. Very hard things are brittle, but it's a different property. Hardness doesn't directly tell you how it handles impact.
So Charpy is the specific test designed for that impact energy absorption, that toughness factor, crucial for safety.
Absolutely critical in many applications.
Okay, fourth question. This one is about a specific flaw type and where you'd expect to find it. Listen carefully. Slag inclusions may be present in manual metal arc welds. B, metal inert gas welds. C, metal active gas welds. D, all welds. All right, linking flaws to processes now. Which welding method is the likely culprit for slag inclusions and why?
This is fundamental process knowledge for any inspector. You need to know what flaws are common to which process. And the clear answer here is A, manual metal arc welds.
MMA or stick welding?
Exactly, stick welding, or SMAW as it's also known. Let's think about slag first. It's that glassy layer that forms on top of the weld bead, right? Because from the flux coating on the MMA electrode. That flux melts during welding, does important jobs like shielding the weld pool from air, and then it solidifies as slag on top. Now, if the welder isn't careful, especially between passes in a multi-run weld, bits of that slag can get trapped inside the weld metal as it solidifies. That's a slag inclusion.
So it's inherent to the flux used in MMA.
Precisely. The flux creates the slag. Now compare that to, say, MIG, metal inert gas, or MAG, metal active gas welding. These processes use a continuous wire electrode and a shielding gas like argon, or an argon CO2 mix pumped over the weld area. There's no flux coating generating slag. So logically, slag inclusions are very, very rare, practically impossible, in standard MIG or MAG welds.
Okay, that makes perfect sense. The source of the slag just isn't there in MIG-MAG.
Exactly. Knowing that Link MMA uses flux, flux makes slag, therefore MMA is prone to slag inclusions, is vital for efficient inspection. You know what to look for.
Great point. Understanding the process helps you anticipate the likely problems. Okay, last question for this deep dive. Let's get into weld zone anatomy. The fusion boundary of a fillet weld is the options A, boundary between the weld metal and HAZ of B, boundary between individual weld runs, wind depth of root penetration, D, boundary between HAZ and parent material. Right, take a moment. Defining interfaces here. Where exactly is that fusion boundary? Why does this specific line matter so much?
This definition is absolutely fundamental. It's about understanding where melting stopped and where heat just well affected things. The correct answer, the precise location of the fusion boundary, is A, boundary between the weld metal and HAZ.
Between weld metal and the heat affected zone. Okay.
Let's visualize it. The fusion boundary is literally the line marking the extent of melting. It's where the molten weld pool solidified against the parent metal that didn't melt. It's the edge of the puddle, essentially. Now, right next to that line in the parent material is the heat affected zone, the HAZ. This area got hot enough for its microstructure, its internal structure, to change. But crucially, it didn't melt.
So fusion boundary equals melted edge. HAZ equals heated but unmelted zone next door.
You've got it. Melted versus just heated. And why care? Because that fusion boundary and the immediately adjacent HAZ are critical zones. That's where you can get specific types of cracks, like solidification cracks right on the boundary, or hydrogen cracks in the HAZ. It's where metallurgical changes are most pronounced. An inspector needs to know exactly where that boundary is to look for those potential issues and assess the overall integrity right at that crucial interface.
That clarifies it perfectly. Knowing those zones helps you pinpoint where potential problems might be hiding. And that wraps up our 5 questions. We've covered core duties, practical tools, material testing, process flaws, and weld anatomy. You've just taken a significant step in your CSWIP 3.1 prep. Hopefully, understanding the why behind these answers gives you a real confidence boost. You are better equipped now.
Definitely. And remember, the standards are your guide, yes. But truly understanding the reasons behind the rules, the physics, the metallurgy, the safety implications, that's what separates a good inspector from a great one. Keep asking why. That critical thinking is invaluable.
Spot on. Deep understanding is the best tool you have. A huge thank you for joining us on this deep dive today. Keep studying, keep questioning, keep building that expertise. This was all for you to help you ace that exam. We'll catch you on the next one.